Suppose there is one problem which I'm trying to solve. Here I'm constraining in this location and putting the load here. And as we can see, this is a tube whose length is so long and its cross section in compared to its length is small. Then we can model it basically with using three approaches. First is like we can just model a 2D cell elements and we can give the thickness here, or we can just model using our 3D elements, or we can model using 1D element. So basically in this problem, we can use 3D elements, we can use 2D elements, even we can use the 1D elements. So if there are too many elements, as we can see in the 3D elements, it will take longest time to solve. In 2D elements, in between that, in 1D element, it will take the shortest amount of time to solve. In 3D elements, as per this element size, we need to solve 8856 into 3 DOFs to solve this problem, as one node contains 3 degrees of freedom. If we go on to the 2D element, uh, we need to solve basically, the software need to solve 2448 into 6 DOFs, as one cell node contains 6 degrees of freedom. But if we model this problem with 1D element, we just need to solve, as there are two nodes, we just need to solve 12 DOFs to solve this problem. Basically, when to use 1D element, whenever there is a length of any geometry is too large as compared to its other dimensions, you can freely use the 2D 1D elements. And but 1D element don't capture detailed 3D stresses across the section. But for most analysis, simple analysis, we can use 1D elements. Even for complex systems also, we can use 1D elements for global load path transfer and stiffness representation. So if this problem uh, we need to model using solid elements, we just need to define the properties, which is PSOLID, and in that PSOLID we just need to define the material as steel. If somehow we need to solve this problem using cell elements, we can just define the thickness in PSHELL card, in PSHELL property card, and obviously the material in PSHELL card we can define. But coming to this element, if we somehow need to model this using C-beam element, then we need to define this P-beam. Then coming to this P-beam, P-beam basically contains these two nodes or beams. We need to define three things. Firstly, the cross section of beam. Second is the orientation of that cross section. And third is the material property. So when to use these beams, we can use, as we have already discussed, where one dimension is significantly larger than the other two. And in most cases in bridges, we can use these beams to model these bridges. We can use these beams to model truss. We can use these beams to model the drive shafts in an automobile. Some of the common misconceptions about beam elements are like the curved beams are not possible using 1D beam element. It is not possible to represent curved beams using 1D beam elements. Or the second one, the most common misconception is varying cross-section beam elements are not possible. So this both are possible using 1D beam elements. We will see in the later section of the video. So if you go to HyperMesh, now there are two options to create. One is a rod category and one is a beams category. In beams also there are two or maybe four types of element types in beams. And if you go to this rod option also, there are four element types. So what to use and when to use, we will discuss now. So coming to C-rod element, it is the simplest type of element. So C-rod element is basically like it is connected by two nodes, and basically it supports axial tension compression and torsion behavior, where we used to define uh, the cross section area in property, and also uh, the torsional moment of inertia, the polar moment of inertia. And the CONROD is a much simplified version of CROD where we don't even need to define the property. Whatever we used to define in CROD property, we will define in the CONROD element itself. So basically, if they both will give you the same result. And RROD is basically a rigid version of CROD, so it's kind of work like an RB2. So nowadays, RROD is not no longer used. Instead, people started using RB2 due to its convenience. One more element we missed here is C-tube element. C-tube element is basically like if there is a tubular section where we are only interested in tension or axial in axial tension or compression forces, or we need to go with torsional analysis, we can easily use C-tube elements. So to compare rod and tube element, we will first create rod element here. So just go on here in 1D and go to here rod, and we will just put C rod here. This node, first node, this will be second node. That's it. So I need this in my rod element. So I will go on here, make current, and I will just go on and uh, transfer this element to this destination. That's it. So this is my rod element. Now I will make this tube as current, and now I will make tube element here. Just go again to 1D rods, and instead of this rod I will put C tube, and this will be my first node, this will be my second node, and yeah, created. So this two are created. If you see here, like I have applied some properties. So this property is nothing but PTUBE, and in PTUBE I just defined the steel property, and I have just 10 as my OD and 1 as my thickness. Secondly, coming to this rod element, what I have defined is PROD as property, and inside this PROD, if you go on here, you will see like I have defined as area of cross section as 1, uh, J as polar moment of inertia, and C as this torsional constant as 1. So these are my settings. Boundary conditions I have applied in two subcases. So in one is just tension. So that means one end is fixed and the other end I am applying the force of 100 newtons. In the second subcase, I am just fixing it here again, and moment I am applying in about x-axis. One more thing is in the output card. Now I just want to print my stresses. So instead of, I'll go to here stress, and instead of plot, I'll just go to print. So this will print the stresses in F06 file. So we have printed the results in F06 file, and now if you see here, this is the element 1. This is the element 1, which is C rod. So if you see here, it is having the area of cross section of 1 Newton per mm. It is area of cross section is 1 mm square. So stress comes out to be 100 Newton per mm square, as we have applied 100 Newton force. Similarly, here also in tube also we have applied 100 Newton force, and area of that tube is this. So stress is coming out to be this. Now coming to the torque, we have applied 1010 Newton mm of moments. So we will go to here, and if we see here, like we are getting the torsional stress of 1 Newton per mm square. Why? Because we have defined as GAS10 and CS1. So its calculations appears to be like this. And coming to tube, if you go to tube here, if you go to tube here, you will see like we need to calculate the polar moment of inertia, which is coming out to be this. And if we calculate the uh, tau, which is torsional stress, it is coming out to be this, which is same as whatever the torsional stress we are getting it here. So to summarize, if there is no bending and only torsion or axial tension or compression, use C-rod element for a solid cross section. Use a C-tube element for a hollow cross section. A CONROD behaves the same as C-rod. If you don't assign a property card, it will give the same result as a C-rod. And RROD works just like an RBE2. Alright, now imagine applying a transverse load at one of the nodes of a C-rod element. What happens? Well, a C-rod can only handle axial forces and torsion. It has absolutely no bending or shear stiffness. So when you push it sideways, it simply cannot react. In the results, you'll actually see zero displacement in that transverse direction because the element doesn't even have the degrees of freedom to deform under that kind of load. And since there's no axial stretch and no twist happening, both the axial stress and torsional stress will come out as zero. That's exactly why a C-rod is only meant for pure axial or torsional behavior. Now, let's look at the cases where bending actually is involved. In these situations, a C-rod simply won't work because it can only handle axial forces and torsion. It has no bending or shear stiffness at all. So whenever your structure needs to resist bending, you have to switch to bar or beam elements. Bar and beam elements are much more capable. They can take axial tension and compression and torsion just like a C-rod, but on top of that, they also handle bending moments and even shear forces. That means they can deform realistically when the load tries to bend the structure, twist it, or push it sideways. So, with this understanding, we have created one truss structure where we have given a pinned support here at this node. So we have constrained all degrees of freedom here, and we have given a roller support at this node. So we have given all degrees of freedom, restricted all degrees of freedom except the DOF1. So it can translate in this direction. And we have using a C-rod element here. I'll show you this. So we have used all C-rod elements here. So there is no chance of bending. And with this load also it will not bend, and that's one of the property of the truss also. So we can easily use C-rod element for the case of truss. And I have given the C-rod property as 1 mm square area of cross section. Then I can easily I have just created one subcase here, and I have used this SPC, this collector as SPC, and this load card as here. And and I have uh, and I have requested the SPC force also. So once we got the output here, we can see here like if we plot the SPC force X, it is 0 everywhere. And if we plot the SPC force Z, it is 0 everywhere. That means that X and Z will have 0 SPC force. So Fy is 100 newtons here, and we want to know why Fy is 100 newtons here. It is quite simple that it is having like if we remove the supports here, we have Fx here unknown, Fy here unknown, and Fy2 here unknown. Now if we take the moment about this axis, we get like Fy2 is nothing but 100. So this is all about the rod elements, and then we will discuss about the beam elements in the next video. Thank you. Have a great day. Bye.